Good morning. Welcome to the third day lecture on design of RCC elements. Today we are going to see about analysis and design of RC beam sections on working stress method. Let me have a brief introduction about the working stress method. As we have seen before in lecture 2 itself, in working stress method it is also called as modular ratio method. It is being ensured by the factor of safety. Here the factor of safety is nothing but the strength of the material divided by your working stress what we are giving for your structure. Then this method is purely based on the modular ratio method and it ensures strain compatibility in terms of steel and concrete, and this method assures you only the linear elastic curve of the stress strain behavior of both the materials, concrete and also for steel structures. Then here in this method the stress strain curve will be only linear. It won't prolong to non-linear part. That's why this method is unrealistic method, but at the same time it ensures serviceability also. That's why this is the oldest method still now we are using for many structures such as water tanks, for proof structures, that is proof structure in the sense containment structures, vessels, water tanks, and for many other structures like that. For example, for dams also we are working under working stress method. Today in working stress method we are going to see about the beam sections. Beam is nothing but a horizontal member in your structure. We have two types of beams. One is singly reinforced beam and another one is doubly reinforced beam. What it means singly reinforced is that we are providing steel only in the tension region, not in the compression region. That is called as singly reinforced. The reinforcement provided as single in the sense in the behavior of single, where compression and tension takes place. The compression is mainly taken care by the concrete and the tension is being taken care by the steel. Where we have putting your steel in tension region alone, we can call it as singly reinforced. Okay. Now doubly reinforced sections. Doubly reinforced sections is that we are providing steel in both compression and tension to take care of something. What does mean that something is right? Doubly reinforced when you have some restriction in your beam depth. For example, this is your beam. We have some certain depth. When a client says that you need to restrict your depth to this level, that is for example 500 mm, it should not go beyond 500 mm. If I am designing a structure, it gets some 600 mm, I need to diminish my depth of the beam. That's why I am decreasing. How I can decrease? By providing something inside it, I can reduce my depth. Providing something is that I can provide compression steel also at the top and provide tension steel also at the bottom level, so that I can manage my beam in some reputed depth restrictions. That's why we can provide doubly reinforced in most of the structures to ensure reduction in cost of concrete and reduction in cost of steel, and also it ensures safety to our structure. Okay, in doubly and singly we can opt three types of sections. Three types of sections is that one is nothing but balanced section. Balanced is nothing but in the name balanced itself we are providing steel which is equivalent to your concrete area, that is the moment of resistance produced by the concrete and the moment of resistance produced by the steel, it is more or less getting balanced. That is called as balanced section. Okay, then under reinforced section. Under reinforced is that the name that denotes under. Under means we are providing the area of steel which is much less than the concrete area. That's why we are calling it as under reinforced section. In under reinforced section, when it is being subjected to loading, what will happen is that the steel part will yield first after the concrete is getting yielded. That's why we can ensure more amount of deflection and we can ensure more amount of cracks in a distributed manner over a structure. It means that why we need to get more amount of deflection and more amount of cracks, so that we can tells that it gives you warning to your structure before failure. That's why this under reinforced section is still now following in our construction industry for making it safer. Okay, what is mean by over reinforced? Over reinforced is that we are putting more amount of steel so that the steel will gets yielded later. Before that, the concrete is being failed. When the concrete is failed, the failure criteria is being described by brittle nature. That's why the brittle failure we should not ensure it in our members. Whereas in under reinforced section and balanced section, the failure criteria is ductile failure, the steel is getting yielded, whereas in over reinforced, the concrete is getting failed than the steel structures, steel reinforcement. That's why it gets brittle failure. That's why in most of the sections we are designing it as under reinforced or balanced section. At the same way, whether we can use balanced section or not, we can't completely ensure that the section is balanced. Mostly we are providing it as under reinforced section only. Balanced means we can't predict that our concrete is made in cast in situ condition, our steel is made in controlled environment. We can't tell it as the yield stress of concrete and yield stress of steel can be balanced in the same way what we are providing it in our elements. Okay, now we are going to see about the analysis of RC beam section. RC is reinforced concrete beam sections, and the design part of your RC beam sections only for singly reinforced beams alone today. Okay, let me have a brief overview about what is mean by analysis and what is mean by design. Some says that the design will first comes and the analysis will proceed that. Some says that the analysis will be at the first and design will be at the second. Let me clarify what is mean by analysis and what is mean by design today. Okay, we'll have some short description about that based on our problems that I am going to work out today. Okay, let us see analysis and design. What will be the given data for the analysis problem? First one, cross section. It is our input data. The second one, grade of materials. For example, if it is concrete M20, we can say. If it is steel, Fe 4 and 5, Fe 500, like that we can give the input as grade of materials. Third one, reinforcement sizes and its location. These are all some of the inputs we are going to give for your analysis problem. Then what is your findings? Findings is that here we are going to check about strength criteria, strength, then stresses, third one, ultimate bending moment, fourth one, shear force. Okay, in analysis part, we have given some cross-sectional dimension, we have given some grade of materials what we are using for this cross-section of the beam, and we have also provided the reinforcement that is being inside our beam. This is our given data. For this given data, what is your strength of the beam? What are the stresses pertaining to your cross-section of the beam? What are the bending moment and shear force taking place for your particular section? These are all some of the outputs or findings belonging to your analysis part. Let me come to the design part. The design part will gives you design load, for what type of load this structure is being constructed. Then second one, applied moment. Applied moment. These are some of the given data given for your structure to be designed. The findings is that we'll get cross-sectional dimension For a particular load, what type of cross-sectional dimension is being adopted? It is being taken care from the design part. Then the reinforcement details. Reinforcement details. These are some of the findings from the load given, from the applied moment given for your member. From this, you are going to calculate the cross-sectional dimension and the reinforcement details pertaining to your sections. This is coming under design. Whether the design is simple or analysis is simple is that the design will get unique answer. You don't get any controversy in your answers, but design you will get some lot of solutions. Lot of solutions in the sense, I can adopt as a design engineer, I can adopt 20 mm dia bars also, or else 16 mm dia bar also, or else I can design my structure for 12 mm dia bar also. It is pertaining to the designer, so that we can get lot of solutions for your design part. Whereas for analysis, you will get some unique answer. It will be so easy for your structural design point of view, whereas the design is somewhat critical. That's why first the stage will start from plan, analysis, design and detailing of your structures. This is the scenario we need to follow during our planning of our structure. First thing, we need to plan your drawings according to your client's consideration. After that, you need to analyze what type of stresses it will be carried out for some assumption of your cross section of your elements provided before it itself. Then after assumption, assuming something the cross sectional dimension, you need to check those values whether that assumptions will satisfy your design part. After that, you can provide some reinforcement. From the reinforcement, you can detail your drawings so that your part of your structural design will be completed. Okay, now we are going to see about some problems related to singly reinforced beam. Problem number 1. The beam of width 250 mm and overall depth of 400 mm with a clear cover CC of 25 mm provided with reinforcement of 5 bars of 20 mm diameter. Adopt M20 and FE4 and 5. Design the beam as singly reinforced section. Calculate the moment of resistance. Okay, now we'll have some drawing for the given picture. The beam having breadth of 250 mm and the overall depth of 400 mm with the clear cover of 25 mm provided with the reinforcement bars (20 mm) dia. The clear cover denotes here is nothing but 25 mm. First, here we need to calculate the values pertaining to the neutral axis. For calculation of the first step involves is that to find depth of neutral axis. This is NA. The depth of neutral axis is nothing but x. It is the depth of neutral axis. To calculate this depth of neutral axis, you need to have some constant values. That constant is that sigma st and sigma cbc. Sigma st and sigma cbc is purely based on the grade given M20 and Fe4 and 5, or else Fe500, or else we can give Fe250 also, Fe500 also. It is purely based on the values in the code book. The sigma CBC value for M20 grade of concrete is 7 Newton per mm square. Then sigma ST value for Fe250 is 140 Newton per mm square. Here I have taken for Fe250, the sigma ST value is 140. This is being taken from table 21 IS 456 2000. Okay, from these are some of the design constants pertaining to our grade of concrete and grade of steel. Now we are going to calculate the depth of neutral axis now. For calculating the depth of neutral axis, the moment of resistance of concrete section should be equated to the moment of resistance of the steel section. For that, B into x by 2 is equal to m times your AST, that is your transformed section, m times your AST into d minus x. D minus x, it is nothing but this area is d minus x. Okay. Now we can substitute the value of B, value of m, value of AST and value of d. Here d, small d is nothing but 400 minus your clear cover value 25 mm minus of the half the times from the top fiber till the centroidal level of steel. This is called as effective depth. So in the problem itself it is given it as 20 mm, so that minus 20 divided by 2, we can calculate it as half of your steel reinforcement, that is centroidal level of steel. This what we can calculate D. Okay. Then how to calculate M? M we can directly calculate it as 280 divided by 3 sigma CBC. We can directly calculate the value. You know what is sigma CBC value. You can directly calculate 3 sigma CBC. Again you can able to substitute here 250 x squared divided by 2, that is equal to 13.33 into pi by 4 into 5 into 20 square. This is the AST, 5 bars of 20 mm dia. 5 is your number of bars. Area of 1 bar is pi by 4 into d square, that is 20 square into d minus x, 365 minus x. Here you will get some equation. It is in the form of x square plus 167.42x minus 6110, that is equal to 0. If you solve this quadratic equation in calculator, you can get the value of x, it as 177.29 mm. This is the first step we need to calculate for depth of neutral axis. Okay, now we are going to step number 2. Step 2, moment calculation. First one, moment due to concrete failure. For that, we will have some design constant. Sigma CBC is equal to 7 Newton per mm square. We can write the formula only for concrete alone. M is equal to B x sigma CBC half into d minus x by 3. That is, from the stress strain curve, this is your C value, this is d minus x by 3 value, sorry, this is x by 3, this value is total d minus x by 3. Moment is that when it is subjected to concrete failure, this load into the distance, load is nothing but the concrete force here C. C is equal to the area of triangle half into base into the height, half 1 by 2 base x sigma CBC value. This is sigma CBC, this is x. It is purely based on your section, that's why we are taking it as B. X half, this one, half base into height, the area of triangle into the distance travelled, that is d minus x by 3. Now we can able to substitute the value of B, that is 250, into what we are getting, x 177.29 into 7 into 1 by 2 into 365 minus 177.29 divided by 3. We can get the answer it as 47.45 kilonewton meter. This is M1. We can keep this as M1. This is failure due to concrete. Then in step number 2, moment due to steel failure. Here we have the design constant is as sigma st is equal to 140 Newton per mm square. We have certain formulas for calculating the steel failure, that is M2. Here we can write M1. M2 is equal to AST sigma st d minus x by 3. That is, this is your top portion, this is above your neutral axis, this is below your neutral axis. We have a tension along steel alone. This distance is d minus x by 3. This is compression C into this. Here we are taking it as T into this. This T is equal to stress in steel due to the area of concrete. So sigma st into AST into d minus x3. This is your lever arm distance. D minus x by 3 is nothing but your lever arm distance. Now we can calculate the value 1570 into 140 into 365 minus 177.29 divided by 3. Now we can get M2 at 67.23 kilonewton meter. Now from these two, M1 and M2, we can clearly define it as the section will fail under concrete or the section will fail under steel. Okay. Here M1 is 47.45, M1 which is less than or M1 which is less than M2. M1 is nothing but concrete which is less than steel. So we can write an expression that this section is governed by concrete. You can ask me what is mean by governed by concrete. When I applied some load, it is being failed for 47.45 kilonewton meter itself. It won't go beyond 67.23. When it is carried by the steel, it is go for 67. The moment which is lesser, it is being governed by that section, so that it is governed by the concrete. So the concrete fail first. Sometimes it is economical also. We can able to see that we are providing more amount of steel, we can check that it is being over reinforced. We can tell like that also. Okay.